Hello again. We're working on our AP free response question number 174. This is a no calculator problem. Just highlight that there to remind us. And we'll read through it here, and then on the next slides we'll go through and solve each of the pieces of this problem, A, B, and C. At time t equals 0, a boiled potato is taken from a pot on a stove and left to cool in the kitchen. The internal temperature of the potato is 91 degrees Celsius at time t equals 0. So we're 91 at t equals 0. That's what we usually call the initial condition. And the internal temperature of the potato is greater than 27 degrees Celsius for all times t greater than 0. The internal temperature of the potato at time t, minutes, can be modeled by the function h. And h satisfies the differential equation. dh dt equals negative 1/4 times the quantity h minus 27. So this is a differential equation. And I want you to notice that there's some interesting pieces of that equation which will come into play here. The derivative is defined by the original function value. So if you think of this function as a y function, then its derivative has a y in it. So this is a good case for what we'll call our separable differential equations when the time comes. And then the last part of the question just tells us that h is measured in degrees Celsius. And then here's that initial condition again written out explicitly. H of 0 equals 91. So that's the setup for the problem. And then we have each of these items that we're going to address, A, B, and C, as we go through the problem. So we'll start with letter A on the next slide and see if we can solve that. So we're going to work on letter A. And you can see letter A says, write the equation for a line tangent to the graph of h at t equals 0. Use this equation to approximate the internal temperature of the potato at t equals 3. So our tangent line is going to be at t equals 0. We'll call that a linearization. And then we're going to use that tangent line to approximate the value at t equals 3. Just to remind you about how tangent lines work, usually what we'll do is we'll use the point-slope form for the equation of a line. That's another way to write out a linearization. So we'll do something like y minus y1 equals m times x minus x1. That y1 is really terrible. Let's see if we can fix that. And so that's how you set up the equation of a line. We know that we need a derivative for slope. The problem with our problem is a weird phrase, but you'll notice that we don't have x's or y's listed in this description of the problem. We have h and we have t. H is serving the role of y, and t is serving the role of x. And then we know that when t equals 0, h equals 91. So that's our initial condition. So eventually when we fill this thing in, the 91 is going to go where the y1 is, and the 0 is going to go where x1 is. So that part's easy enough. What we don't have is the value of the slope. But you know as well as I do that the way you figure out slope is just with a derivative. And we do have the derivative right here. Our derivative formula is dh over dt equals negative 1/4 times h minus 27. Well, we said h was 91, so what we're going to do is plug that in. So for us, we're going to do negative 1/4 times 91 minus 27. And 91 minus 27 is 64, so this is negative 1/4 times 64. 64 divided by 4 is 16, so the slope is negative 16. Okay, so we're asked to write the tangent line. So for that, I'm going to do y minus 91 equals negative 16 times x minus 0, so times x. And then we'll just solve for y to make it look official. So this is negative 16x plus 91. That's our tangent line. Okay? And we have to use this linearization, this tangent line, to approximate the value of the function at t equals 3. So we're going to plug in y equals negative 16 times, we'll plug in 3, and we'll see what we get here. So what is that? Negative 48, 91 minus 48. So that's going to be 43. So when we do this problem, we end up approximating the value at, we'll call it 43 degrees Celsius, because h is measured in degrees Celsius. And remember, y is really h that we solve for. So to get the equation of a tangent line, you need an initial condition and you need a slope. They gave us the initial condition right here. And then we use the derivative to compute the slope. The thing that's weird about this derivative, well, it's not weird, but it's something to keep an eye on, is that the derivative is defined with the h variable, not with the t variable. So you don't plug in t values, you plug in h values. And we did that, and we've got our slope here, and then we used it in our equation. And ultimately, we did the approximation of 43 degrees. We'll tack letter B on the next slide. So we're going to talk about letter B here, and it says use the second derivative, d2h over dt2, to determine whether the answer in part A is an underestimate or an overestimate. Let me just talk real quickly about what that means. So remember, we did a linearization. So we took a tangent line to the curve. All right, so it's an underestimate if the picture looks like this. And that's a terrible picture. Let's see if we can, if the picture looks like this, where the tangent line comes through like this, and it's below the function. So the blue one is the actual function, and the black line is our tangent line. And so you can see when the function is concave up, right? When this is concave up, then we are under the curve. We're an underestimate. However, if our function was concave down, our tangent line would be above the curve, and that'd be an overestimate, right? Because it's higher. That's a terrible graph too. But when we're concave down, we'll have an overestimate. This is over, and this is under. Okay, so essentially what we want to know is the second derivative positive or negative? So let's go ahead and figure out that second derivative. Remember that we were given the formula for the derivative right here. dh over dt equals negative 1 over 4 h minus 27. And in fact, if you don't mind, I'm going to distribute that, make it negative 1 over 4h plus 27 over 4. Oops. Yep. Okay. Now remember, we can think of this as h prime if you want. Remember that this is not an explicit function. This thing's defined implicitly. In other words, we've got y stuff over here, right? So when we're doing the derivative, again, right, we're trying to find the second derivative, which is h double prime. We take the derivative of negative 1/4 h, which is negative 1/4, but then we have to multiply by the derivative of h prime, or in the notation of Leibniz here, we'll do dh over dt. And then this derivative here is just 0. So the negative or the positive 27 over 4 turns into 0, but our derivative but our derivative, our second derivative, is defined in terms of the first derivative. Now, we already know what the first derivative is, so let's just write that out. So this is my second derivative. Oops, let's not use that color. Let's do d2h over dt2. That's going to be negative 1/4 times the original up here, which was negative 1/4 times h minus 27. Okay, and when we distribute this, we're going to get 1/16, because negative 1/4 times negative 1/4 is 1/16. So that's 1/16 h minus 27 over 16. All right. Now we have to go back up to the written description here and notice that it tells us that the temperature is greater. Oops. I'm having one of those days. I want the highlighter here. The temperature is greater than 27 degrees for all the times greater than 0. And so when we plug a value in for h right here, this guy is greater than 27, meaning that this fraction is bigger than this one. And so this is going to be positive. That means that we have this situation, and therefore we have an underestimate. So we're going to answer letter B by saying that we have an underestimate because we computed the second derivative, and no matter what temperature we plug in there, that value is going to be positive. So the function's concave up, and that means the tangent line comes in below the function. All right. We'll wrap this video up by attacking letter C on the next slide. As we attack letter C here, we finally get to use those separable differential equations that I mentioned at the beginning of the video. For T is less than 10, an alternate model for the internal temperature of the potato at time t minutes is the function g. And here's the differential equation for g. So we've changed the formula. H has a different formula than g. G of t is still measured in degrees Celsius, and we have the same initial condition. So we still have g of 0 equals 91. We are supposed to find the expression for g of t. And then based on that model, what's the internal temperature at t equals 3? Now, all we have is the derivative. To get back to the original function, we have to do what we know as an antiderivative, right? But this is a differential equation. The derivative is defined in terms of the function value. So we're going to need to perform separable differential equations to get back to g. And then we'll solve for the plus c using our initial condition. All right, so let's see if we can do this thing. We have this derivative, dg over dt, equals negative g minus 27 to the 2/3. When we do the separable differential equations, remember we learned essentially that we want to get all the y stuff on the left and all the x stuff on the right. For us, remember, g is actually y. G is playing the role of y. And t is x. Well, this thing doesn't have any t's in it. It only has g stuff. So we're going to bring all of the g stuff over to the left, and then we'll just move dt over to the right on its own. And you can decide where you want the negative sign. I think I'm just going to leave the negative sign over on the right side. So let me see if I can get through this algebra with you. We are going to divide by the g minus 27 to the 2/3. So that would look like this. And we're going to multiply by dt. So this would be like a negative 1 dt over here. And then the technique for separable differential equations is that we're going to do the antiderivative on both sides. Okay. So the antiderivative on the left is pretty straightforward. This is just, on the right. This is negative t. And remember, we just put our plus c over on the right. There'll be two plus c's. We mix them together and put a new plus c on the right. On this side, it's a composition. You'll notice that the derivative of g minus 27 is actually just 1. So this is really very similar to a u to the negative 2/3. But the dg and the du are the same. So u to the negative 2/3, the antiderivative would be u to the 1/3 divided by 1/3, or 3u to the 1/3. So when we write this out, this is just going to be 3 times u, which is g minus 27, to the 1/3. And then we need to solve for c, and then we need to solve this thing for g. All right. So remember that we've got this initial condition. When t is 0, g is 91. So we'll go ahead and plug that in, just so we can solve for c, and then I'll show you how we can finish this thing off. I don't know why I'm writing sideways. That's unproductive, but let's see if we can straighten it out. So we're going to do 3 times 91 minus 27, which we already know is 64. And we're going to take the cube root of that. And then this is just negative 0 plus c. So essentially there's just c on this side. So when we figure out this answer, we're just going to solve for c. Let's see. The cube root of 64 is 4, and 4 times 3 is 12. So c equals 12. That tells me that the equation looks like this. So I'm sorry, I'm going to work from right to left here, but we're going to continue working over here. We have 3 times g minus 27 to the 1/3 equals negative t plus 12, or you can write 12 minus t. Okay. And then we need to solve for g. So we're going to divide both sides by 3. And then we'll also take the cube root. No, we're going to cube it, right? Yeah, we cube it to... And so my g of t, with that initial condition, it's 12 minus t over 3 cubed. And that applies just up to 10 minutes. Yep, t is measured in minutes, and this thing applies for the first 10 minutes. Now, that was a lot of math. We had to solve the separable differential equation. We had to be careful with the composition. We had to solve for c. And then we had to solve for our function g. So there's a lot of stuff going on here. Math teachers call that a content-rich problem. Well, that's the explanation. Hopefully you were able to follow it. I'm sorry I worked from right to left instead of left to right. If you have questions, you know where to find me. Good luck.